So thanks for the invitation for this fantastic webinar. So in this presentation, I would like to give you a brief introduction about one of my recent work, which is about understanding the extreme nanoscale confinement of light of this cavity with our developed model analyzed tools of our group. So let's begin our talk by studying this this tuning fork. We see from this figure that for this tuning fork, after if we strike this tuning fork after this initial strike, if you wait a little bit, this tuning fork is oscillating in a fixed frequency and damps exponentially. Here we say that the response of this tuning fork is dominated by the excitation of its resonance mode and with a complex eigenfrequency, of which real part is determined by this oscillation frequency and imaginary part given by this damping rate. We say this tuning fork are non-Hermitian system, and such a resonance modes with a non-vanishing imaginary part of eigenfrequency, the quasi-normal mode. So similar to the tuning fork system, for optical cavities, the non-Hermitian optical cavities are largely different from the Hermitian cavities. So basically, the Hermitian nanocavities have been widely discussed in all textbooks. Basically, we know that the Maxwell equation, which determine the resonance modes of the Hermitian cavities, are self-urgent, which leads to their eigenfrequencies to be real number, and their eigenmodes are orthogonal, and they form a complete basis. So that the mathematics of these Hermitian cavities are very simple. On the other hand, the story for non-Hermitian cavities are not quite simple, since that in this case, the Maxwell equation determines the resonance modes are no longer self-urgent, and which leads to, and due to the potentially existing absorption loss or radiative loss, the eigenfrequency is a complex number. And because of this, the eigenmodes of these non-Hermitian cavities are non-orthogonal. And the non-orthogonality of the modes of the non-Hermitian cavity gives us a lot of mathematical difficulties. However, it also provides us a lot of opportunities to explore new physics. For example, the observation of the exceptional point or the observation of the PT symmetry breaking phenomenon. So despite these mathematical difficulties of the non-Hermitian cavities, we know that after years of endeavors of efforts of our groups and also the groups all over the world, people have managed to directly relate the response of any given optical resonator with the excitation of their quasi-normal modes or resonance modes. So here in this expression shows the essence of this model analyzed method. Basically, it says that for any arbitrary response of the cavity, we can expand it can be expanded as a weighted sum over the weighted sum of the excitation of the resonance modes of the cavity. With the excitation coefficients can be analytically computed. And this offers us a tremendous computational efficiency and physical insights. So to illustrate the powerfulness of this model analyzed formula, let us consider this simple system, which is basically a dolmen-like structure formed by 3 metallic nanorods. We consider the case where this dolmen-like structure is shined by a pulse. And as is well known that for such a system, one can easily compute the response of such a domain structure using some temporal-based method, like the well-known FDDT method. However, however, the FDDT method provides us little physical insight. So in principle, we don't know the response of we don't know which are the modes which dominate the response of this domain-like structure, and we don't neither we know that neither we do know how much these modes are excited. On the other hand, by using our model analyze method by computing only three resonance modes of this domain-like structure in the visible wavelength range and computing their corresponding excitation coefficients, we were able to exactly reconstruct the response of such a domain-like structure, which offers us a lot of physical insights and computational efficiency. So in the remaining slide, I will give you a brief introduction about my work, which is about to offer a new explanation of extreme light nanoscale light confinement of this cavity. So basically, this slide has been shown by Philip, gave the background of this work. It shows the evolution of optical cavities for light confinements over the past 2 decades. Basically, the evolution starts with the nanocavity, and then with the advent of plasmonic material, it is possible to confine light in volumes which are orders of magnitude smaller. And then in 2016, the Cambridge group led by Jamie Bomber reported this Pico cavity, and they found that inside this Pico cavity is able to offer a light confinement, is able to confine light in a volume about 1 cubic nanometer, which is orders of magnitude smaller than all of these systems. And also from this slide, we can find that the capabilities of this nanocavity to confine light is characterized by 2 figures of merit. One is the quality factor, and the other is the well-known mode volume. However, besides these 2 figures of merit, there's another figures of merit. Merit to characterize the capability to their optical confinement capability, and it is the brightness. So basically, the brightness of optical cavity is defined as the ratio between the radiated energy of the ratio between the radiated energy and the total energy scattered by this optical resonator when it is excited by a when it is resonant excited by a source. So that we know that for simple sub-wavelength nanocavities, like simple metallic nanorods or nanosphere, basically we can analytically prove that their mode volume, their brightness is proportional to the brightness. So one fundamental aim of a lot of work consists in designing optical cavity, which is capable of offering both small model consists in in designing optical cavities, which is able to break this relationship and is able to provide some modes which is able to offering both extremely large brightness and extremely small mode volume at the same time. So, so later we will say that the Pico cavity proposed by the Cambridge group actually has this remarkable feature of providing both extremely large brightness and a small mode volume. So this figure illustrates the structure considered by the group. And basically, it is basically a nano cavity and consisting with this metallic tip attached on the upper surface of this nanoparticle. So in their work, they insert some molecule inside the gap of this nano cavity and measure the surface enhanced Raman scattering. And in addition, detecting some convention Raman signal, they also detect some Raman inactive signals, which would otherwise require the mode volume of such a cavity to reach a value about 1 cubic nanometer. However, we know that from this figure for a convention nanocavity, it can only basically provides a mode volume about 1,000 cubic nanometer. So in this work, they attribute this additional field confinement capability of this cavity to an atomic scale lightning rod effect. So what is the lightning rod effect? So the lightning rod effect is basically refers to a non-resonance enhancement of electric field by the sharp tips when it is excited by an electric field parallel to its axis. And it is a well-known physical phenomenon and exists at all frequency, from radio waves to optical frequency in surface plasma tapers. And for this system, in fact, the metallic protobaryons actually act as a tip, and which is excited by the gap plasma of this nano gap cavity. So that in this case, when such a Pico cavity is excited by an external plane wave, the overall field enhancement is determined by the enhancement factor offered by this gap plasma cavity and the enhancement factor given by the lightning rod effect of these metallic protobaryons. So in our work, although this non-resonant lightning rod effect is very interesting, in our work, however, we otherwise do not attribute this additional field enhancement factor to this non-resonant lightning rod effect. We otherwise noted for such a protobaryons on a metallic substrate, its second interface can actually act as a perfect mirror, which is able to perfectly reflect the surface plasma launched on this protobaryons. So that in this case, when a surface plasma is launched inside the volume of this protobaryons, it is able to bouncing back and forth between the two interfaces of these protobaryons, and this giving rise to some resonant field enhancement effect. So to understand the response of protobaryons on a substrate, we model it as a shape, as a hemisphere, and compute its resonance mode. So here, here we model the protobaryons as a hemisphere. However, what I'm going to say below is quite independent with the shape of the protobaryons. So here are some takeout informations about the resonance modes of these protobaryons. First is that indeed, in the concerned frequency wavelength range, we can indeed find from very interesting resonance modes, and all of these modes have supports a mode volume which can reach an orders of magnitude of the geometry volume of this protobaryons. And in this case, considering the geometry volume of this protobaryons is extremely small, the mode volume of this resonance modes can easily reach a value about let's say 1 cubic nanometer. Another takeout information about the resonance mode is that its quality factor is also very high, which can reach a value about few tens, which is about the quality factor of a convention plasmonic nanocavity. On the other hand, I want to mention that the physics behind the formation of this resonance mode is actually quite easy, and they can be easily interpreted with a simple Fabry-Pehot model. Here M denotes the famous round trip numbers of round trip of the Fabry-Pehot model. Here in this figure, we compute the resonance modes of this protuberance structure as a function of this thickness. As can be seen that we can achieve a good agreement between the analytical prediction provided by the Fabry-Pehot model and the numerical results. So as has discussed before, that the metallic protuberance on a substrate is able to support some high quality mode with extremely small mode volume. However, like a traditional plasmonic structure, their brightness is proportional to the mode volume. Therefore, in this case, their brightness is vanishing when the model volume is about 1 cubic nanometer. On the other hand, we note that for convention nanocavity, they automatically supports a lot of modes with, although a relative large mode volume, they can provide extremely high brightness, which reach a value about 10%. So one natural question, a natural question one may ask is that if we are able to combine these two structures to form a hybrid cavity, are the modes of this hybrid cavity is able to take the advantage of the modes of both of these protuberance mode and the nanocavity mode, and provides both very extremely small mode volume and extremely large brightness. So our numerical calculation gives a positive answer to this question. Here in this figure, we compute the resonance modes of this hybrid cavity as a function of the aspect ratio of this protuberance. Basically, we can find that in this wave coupling region, we can identify two modes. One mode is very similar to the nanocavity mode with a relatively large brightness and very large and a relatively large mode volume, and one is very similar to the protuberance mode. On the other hand, in this strong coupling regime, we can identify two hybrid modes, which is able to take the advantage of both of these two modes, bearing both a large brightness and extremely small mode volume. And also, this hybridization phenomenon can also be identified from the near field distribution of this mode. It can be seen that in the vicinity of this protuberance, the electric field is strongly enhanced, which is very similar to this protuberance mode. And also it has the feature of this nanocavity mode with no vanishing electric field inside the gap. So in order to understand this hybridization phenomenon inside this cavity, we otherwise consider a simpler structure. We first consider an isolated protuberance on a metallic substrate. And when we put an emitter in the vicinity of this protuberance, as the brightness is extremely small, we know that all the energy emitted by this molecule or emitter will be absorbed by the resonance mode of this protuberance. On the other hand, if we add this second interface, and the whole structure gives rise to an MIM structure, and it offers an addition channel for the energy for the localized energy from the protuberance modes to decay into. So that for this waveguide system, we can define its brightness as the ratio between the total emitted energy of the molecule to the between the energy emitted into this gap plasma to the total energy emitted by this molecule. And from some analytical derivation, we can basically find that the efficiency for the energy which can be transformed to the gap plasma is basically proportional to the volume of this the side of this protobarons, and inversely proportional to the cubic of the gap of this waveguide. So this formula tells that for any sizes of protobarons, one can always find the corresponding nano gap cavity with a certain size, which gives rise to, which guarantee a strong coupling between the protobarons mode and the gap plasma modes, and offering a hybridized mode with both small mode volume and large brightness. And this analytical formula has been proved with our numerical calculation, as can be seen from this figure. So in conclusion, so in this presentation, I first introduced the quasi-normal modes, introduced some basic concepts of quasi-normal modes of the no-Hermitian cavities, which provides us tools to evaluate the capabilities of different optical cavity, of the capabilities of optical cavities for light confinement. In the second part of this presentation, I gave a brief introduction about my latest work, which basically provides a new explanation for extreme light confinement in the so-called Pico cavities. And in the end, I would like to acknowledge Philippe Lalande, the group leader who supervised this work, and also Wei Yan from Western Lake Institute of China, who helped a lot on the numerical calculation. And at last, I would like to thank you for attention.